All right, we're going to get more practice doing those in a second here, but we just have to introduce one more slightly interesting complication here. It's actually not a different calculation. It's just something that we need to know about a certain type of problem that we have. It involves what we have to do if we're given masses of two reactants and are asked for a product mass. Look at this question right here. 17.3 grams of phosphorus are reacted with 15.4 grams of O2. Those are the amounts of reactants that are available to us. Say we just put those amounts in a container and allowed them to react. And we want to know how many grams of product we can do. Well, if we were just given this one, we could pretty easily calculate how many grams of product just by doing grams to moles to moles to grams. If we totally reacted 17.3 grams of phosphorus, we could figure out how many grams of P2O5 that would create. Let's start by making that little diagram here. So that's 17.3 grams of phosphorus, and we ultimately want to know how many grams of P2O5. Okay? Well, we're going to do like we did before, grams of phosphorus to moles of phosphorus. Way over here, moles of P2O5, grams to moles to moles to grams. Okay? That would be just a linear sequence, just like we did on the last page. The additional piece of information here is that we're also told how many grams of O2 we have available, 15.4. So what we're going to do is start a second calculation with this other piece of information we're given. Grams of P, grams of O2. We're going to convert grams of O2 into moles of O2. And then we're going to convert that into moles of P2O5 and into grams of P2O5. Once we get to this point, we're going to sort of have two answers, and we'll have a decision to make at that point. Okay? And we'll talk about that when we get there. But first, let's talk about what this problem is. We consider this to be called a limiting reactant problem. That means that one of these two reactants will be consumed before the other. No matter how carefully we try to control the amounts, there will always be one of them that will get used up before the other one. That's because they combine with each other in a fixed ratio, and one of those will always get used up before the other. No matter how carefully we try to control it, there will always be some left over of one of them. Okay? And once one reactant is consumed, what do you suppose has to happen? The reaction stops. One way to think of it is like an assembly line. I've got this picture here. This is, I think, from the original Ford Model T plant, one of the first uses of a factory assembly line, where each person has their own bucket of parts and their own job to do. They'll put something on the unit and then slide it along to the next person that adds their part on. But, each person sort of depends on the previous person to have it. So think of this long assembly line. Think about what would happen if one of those people, if their bucket ran out of the part that they're doing. If everybody's moving along, and if the people further down the line depend on this part that you've added, then the assembly line stops. So all it takes really is one person to run out of their bucket of parts for us to be unable to produce complete cars or complete products, whatever it is we have here. Okay? So it turns out that whichever of these ingredients, these are sort of the ingredients, the phosphorus and the O2, whichever the ingredients runs out first, whichever one is consumed first, we call that the limiting reactant, and that's actually what determines how much product we can make, because as soon as any one of the reactants runs out, the reaction stops, and the amount of product that we have there is the maximum that we can possibly get. Let's start this calculation with the phosphorus. Let's set up that grams to moles to grams. Start with 17.3 grams of phosphorus and set up 3 fractions like that. Do grams to moles to grams. You'll end up with some answer that's in grams of P2O5. Okay? And then once you've got that, I want you to start again, but this time using 15.4 grams of O2. Set up 4 fractions. Get an answer that's in grams of P2O5. Like I said before, we'll have to make a decision once we get to that point, but let's start by just filling out these 2 calculations. See if you can get those filled out. See if you can get 2 answers for grams of P2O5, doing the same type of calculation we did before. Make sure in both cases you're ending with P2O5. Okay? You'll have a molar mass, you'll have a mole ratio, you'll have a molar mass. So why don't you pause me now, see if you can fill those out. All right, so we're first going to go grams of phosphorus to moles of phosphorus. Its molar mass from the periodic table is 30.97 grams per 1 mole. Okay. So next we do a mole ratio, moles of P to moles of P2O5, the substance that we're being asked about, and those numbers will again come from the coefficients, 4 moles of phosphorus to 2 moles of P2O5. Then moles P2O5 to grams. The molar mass of P2O5 I calculated as 141.94. Okay. The answer I got for that one was 39.6 grams of P2O5. If you got that, great. If you did not get that, maybe pause now, take a look at these numbers, punch it into your calculator one more time, make sure that you can get that answer. Okay. Try to figure out what it was that went wrong. For O2, we're going to do grams of O2 to moles of O2. Because the formula is diatomic like that, because it's O2, I need 2 O's, so that's 32.00 per 1 mole. Mole ratio, we'll go moles of O2 to moles of P2O5. The coefficients in that case are 5 moles of O2 to 2 moles of P2O5. Okay. And then this last one will look just like it did up here, 1 mole of P2O5 to 141.94 grams of P2O5. And the answer I got for that one is 27.3 grams of P2O5. Okay? So the thing is, we're not quite done yet because we can't have 2 answers. That's a mistake I see a lot of students doing. They go through all the work, they do everything right, but then you don't do the last step, which is actually answering the question. The question is, how many grams of P2O5 can we form? And we cannot form 39.6 and also 27.3. Okay, we're going to have to pick. So to think about how this works, we can use another analogy, like a cooking analogy. Say you're making pancakes, and the recipe calls for, I don't know, a certain number of eggs, so many cups of flour, so much water, so much oil, right? So different numbers for all those things. If you wanted to figure out how many pancakes you could make with all of your ingredients, you're probably not going to be using up perfectly every single one of your ingredients. There's probably going to be one ingredient that you will run out of before the other ingredients. Okay? So what you can do is you can look at each of your ingredients individually and think, if I used up all of this, how many pancakes would that make? If I used up all these eggs, I have enough eggs here to make 10 pancakes. Well, I have enough flour to make 20 pancakes. I have enough oil to make 100 pancakes. Okay? In that case, it doesn't matter that you have enough oil to make 100 pancakes because you would have run out of eggs way before that. Okay? It only depends on the one ingredient you're going to run out of first to determine how much total product you can make. So, let's look at this one right here. In this example, what's going to happen as soon as 27.3 grams of P2O5 are formed? This calculation said that if we used up that 15.4 grams of O2, that would make 27.3 grams. So, the instant we hit 27.3 grams, that's when the O2 runs out. Okay? So, what we're actually going to do here, it doesn't matter that we have enough phosphorus to make 39.6 grams because we're never going to get that far. I want you to cross this one out. That larger value does not matter to us because the maximum we can make is right there. All we did was choose the smallest answer. Okay? We picked the smallest number of pancakes that we could make based off of our ingredients, because that's when we'll run out of something. So maybe go back up here, because I had both of these paths leading to grams of P2O5. We just need to choose the smallest answer. Okay. And I suggest crossing out the other one. That 39.6 is meaningless to us because we will never get one bit past 27.3. Right? So, which of these two is the reactant that runs out first? Well, it's the O2. Let's write that. O2 runs out first. Because it produces the smallest product mass. Another way of saying that is that the reaction stops when 27.3 grams P2O5 are formed. Okay, let's just say product. Another way of saying this is that O2 is the limiting reactant. O2, that's right, LR under it there. O2 is the limiting reactant. We know that specifically because we calculated how much product could be formed if all of that O2 were used up. And we did the same thing for the other reactants. The O2 is the one that made the smallest amount of product, which means that will be the first one that runs out. Remember, we're starting with 0 grams of product. We're building up product, and as soon as we get to 27.3, that's when O2 runs out, and that's when the reaction stops. Okay? So that's what you need to do anytime you're given a problem where you're given multiple reactant masses and are asked for a single product mass. You need to start with each reactant mass you're given, calculating to the mass of a common product. And whichever of those reactants produces the smallest amount of product, that's the limiting reactant. And that smaller answer, that smallest answer, is how much product we could produce. Okay? In this case, it makes no difference at all what these masses are. Okay? It doesn't matter that one is bigger than another or whatever, for a lot of reasons, right? First of all, they have different molar masses. Okay? And secondly, they have different mole ratios. We could need a lot more of one reactant than another just due to the balancing. We could need a lot more of one than another just because one thing has a much higher molar mass, for instance. Okay? So the size of those numbers is meaningless to us. That's why we have to calculate the amount of product. That would be like saying, you know, in your recipe you just pick the smallest number of things, even though you need different amounts of stuff. Okay? So that doesn't matter. You have to figure out how much product each of those could make, because you need a different amount of each of the things, and maybe their units are different or something too. So